Hey there. Tonight we're going looking for the biggest object in the universe, and I can almost promise you've never heard its name. It is around 10 billion light-years across, which means it spans close to a tenth of everything we can see. And it isn't drawn in stars or galaxies, but in explosions, the brightest explosions to happen anywhere since the Big Bang itself. On a clear summer evening, you can stand in your garden and point your finger at the exact patch of sky where it hides. It's so large that according to the universe's own rulebook, it shouldn't be able to exist. And here's the strangest part of all. The astronomers who found it are still arguing about whether it's really there. So tonight we are going to climb all the way up to it, one gentle rung at a time, from your bedroom ceiling to the edge of everything we can see, and find out how you discover something that big, why it has the most forgettable name in astronomy, and why the biggest thing ever found might turn out to be a beautiful trick of the light. If these journeys help you rest, a like or a subscribe is the kindest way to say so. And leave a comment with where in the world you are drifting off from. It's always bedtime somewhere. For now, dim the lights and settle in. I'll keep watch. Now, you're lying somewhere quiet with the window open and the night sky is waiting just outside it. Let's begin. I want you to think about your own ceiling, because every journey to the edge of the universe starts under one. Above it there is a roof, and above the roof there's a sky. And the sky tonight is doing what it always does, which is pretending to be small. That's the sky's oldest trick. It hangs over your street like a dark blanket pricked with lights. All of it seemingly close enough to touch. And for most of human history, nearly everyone believed exactly that. A dome, a ceiling for the world. Something a determined bird might reach. The whole story of astronomy is really just the slow, patient discovery of how wrong that feeling is. And tonight's journey is that discovery told in a single night. Because to find the biggest object in the universe, you first have to learn how the universe does big. It doesn't do it all at once. It does it in layers. Each one so much larger than the last that the numbers stop behaving like numbers and start behaving like poetry. So we are going to climb it the way you'd climb a long staircase in the dark, one landing at a time, resting on each one, until we reach a landing near the very top where something enormous is waiting, something with a clumsy name and a genuine mystery attached. The first landing is the one you know best. The moon hangs about 380,000 kilometers from your pillow, which sounds far until you realize that people have actually been there and that their footprints are still pressed into the grey dust right now. Unchanged after more than half a century, because there is no wind on the moon to sweep anything away. Light makes that trip in a little over a second. Keep that idea of light as our measuring tape, because it's the only tape long enough for where we're going. Everything from here on will be measured not in kilometers, but in the time light takes to cross it. And light is not slow. Light could circle the entire Earth 7.5 times between 2 beats of your resting heart. Before we leave the neighborhood, spend one more moment on that quiet lunar detail, because it sets the tone for the whole night. Those footprints endure because the moon has no weather at all. No wind, no rain, no seasons worth the name, and it makes the moon a kind of museum. The boot prints, the flag stands, the fallen cables, the little metal platforms, all of it sits exactly where it was left, slowly gathering micrometeorite dust at a rate so gentle that the prints may remain legible for millions of years. There is something restful in that. Down here, the tide erases a footprint in an hour. Up there, the universe files things away and forgets to throw them out. Keep an eye on that habit, because tonight ends with the universe having filed away something 10 billion years old, and us only just now opening the drawer. The sun is 8 light minutes away. That is the second landing, and it comes with a thought worth keeping under your pillow. The sunlight warming your face at breakfast is always 8 minutes old. You've never once seen the sun as it is, only as it was, a few minutes ago. The universe has a built-in delay, a gentleness, really, because it means looking far away is the same thing as looking back in time. Remember that, because at the top of tonight's staircase, that little delay becomes 10 billion years. And the thing we are climbing toward will turn out to be not just far away, but long ago. And since light is now our tape measure, let's take a moment to respect a single light year, the unit the rest of tonight is built from, because familiarity has worn it smooth, and it deserves its edges back. 1 light year is the distance light covers in a year, and light covers 300,000 kilometers every second. Written out in kilometers, a light year runs to nearly 10 trillion, a 1 with about 13 digits trailing it. If you drove there, motorway speed, no service stations, it would take you something like 10 million years. If you took the fastest aircraft humans have ever flown, still millions of years, our whole noisy, brilliant civilization, every rocket and probe and triumph of engineering, has so far sent its farthest emissary roughly 1/400th of a single light year. And tonight's destination is 10 billion of them laid end to end. That's the staircase we're on. Every landing from here climbs by leaps that make the last leap look like a doorstep. So, hold the tape measure loosely and let the numbers become weather rather than arithmetic. Past the sun, the landings spread out fast. Neptune, the last of the planets, sits around 4 light hours away. The Voyager probes, the farthest things human hands have ever built, have been flying for nearly 50 years and have barely reached 1 light day. And then comes the part of the staircase that humbles every spacecraft we've ever made, the gap. The nearest star apart from the Sun, the Alpha Centauri system, waits more than 4 light years out. At the speed the Voyagers travel, that single step would take more than 70,000 years, 4 light years, and that's the distance to our next-door neighbor, the closest star in a galaxy that holds a few 100 billion of them. Between the planets and that first star lies one more landing, and it happens to be an old friend of this channel. The solar system does not end at Neptune. Past the planets stretches the Kuiper belt of icy worlds, and far past that, wrapped around everything like the glass of a snow globe, drifts the Oort cloud, a vast thin sphere of perhaps 1 trillion sleeping comets, reaching something like a light year and a half out into the dark. A light year and a half, and it's still ours, still loosely held by our sun's patient gravity, still technically the suburbs. When you hear that the nearest star is 4 and a bit light years away, remember that our own front garden runs 1/3 of the distance there. The universe rarely draws hard borders. It prefers long, soft fades. And tonight we're going to ride one of those fades farther than usually seems reasonable. There's one more idea to pick up on this landing, and it is the one the ancient world would have found most upsetting. The stars you can see are not pinned to any dome, and they are nowhere near one another. Look up at any constellation, and you're looking at a coincidence. The stars of the Plough, or the Belt of Orion, or the summer shapes we will meet at the top of tonight's climb, are scattered across wildly different depths, some a few dozen light years out, some many hundreds, and they hang together as a picture only from this one particular porch in the galaxy. Shift your viewing chair by a few dozen light years, and every constellation ever named would come apart like a bead curtain in the wind. Our ancestors looked at that scatter and drew heroes and crowns and hunting dogs, and they weren't foolish to do it. They were doing what human minds do best, which is finding shapes in scattered light. File that instinct away somewhere comfortable. It comes back at the very top of the staircase tonight, wearing a lab coat. And here's where tonight's method reveals itself, because notice what just happened to the numbers. A second to the moon, minutes to the Sunday hours to Neptune, years to the nearest star. Each landing didn't just add to the last one, it multiplied it. And the multiplying has only started. The universe is built like that all the way up, scale stacked on scale, and the human mind was not really made to climb this staircase. Which is exactly why it makes such good company at bedtime. Somewhere past the 3rd or 4th landing, The part of your brain that keeps score simply lies down in the stairwell and goes to sleep. And what's left is the part that just enjoys the view. Tonight, that's the part we want. So let the stars pour in now, because the next landing is the galaxy, and the galaxy is where the sky first starts to show its true architecture. Every star you have ever seen with your bare eyes, every single one, from the handful over a city car park to the few thousand over a desert campsite, belongs to one building, the Milky Way. It is a flat spiral of a few 100 billion stars, roughly 100,000 light-years across. And we live in one of its quiet, outer avenues, about 26,000 light-years from the bright downtown at its center. When you see that faint milky band arching over a dark summer sky, you're not looking at something in the galaxy. You're looking along the galaxy, down the length of the disk from the inside. The way a fish might look down a river, 100,000 light-years is our first properly unimaginable number. So let's build tonight's first scale model and make it behave. Shrink the entire Milky Way until it fits on a dinner table. A glowing spiral the size of a large pizza. On that pizza, our whole solar system, the sun, all 8 planets, the comets, everything the Voyagers will ever reach, is far smaller than a single grain of dust. The 4 light-years to Alpha Centauri, that 70,000-year voyage, is about the width of a human hair. Every human being who has ever lived has lived on that speck of dust. And every star every human has ever wished on is just another crumb of light somewhere on the same pizza. And the pizza has a few 100 billion crumbs. Now here's the thought that carries us up the next flight. For a long time, right up into the 1920s, most astronomers believed that pizza was everything. One galaxy, floating in an infinite dark, the universe and the Milky Way being simply 2 names for the same thing. There were little smudges in the telescopes, faint spiral wisps that did not look like stars, and the great debate of that era was about what those smudges were. Clouds of gas inside our galaxy, said one camp. Other galaxies entirely, said the other, island universes of their own, impossibly far away. The argument was settled in 1924 by a quiet, pipe-smoking man named Edwin Hubble, and the tool he settled it with had been forged years earlier by a woman almost nobody thanked at the time. Her name was Henrietta Swan Leavitt, and she worked at the Harvard Observatory as a computer, which in those days meant a human being, usually a woman, paid a few cents an hour to measure star after star on glass photographic plates. The men ran the telescopes. The women did the arithmetic. Leavitt's assignment was a particular family of flickering stars called Cepheids, stars that brighten and dim in a steady heartbeat rhythm, and while cataloguing thousands of them, she noticed something nobody had ever noticed. The slower a Cepheid's heartbeat, the brighter the star truly was. That little rule, scribbled out of years of patient measuring, is one of the most important sentences ever written in astronomy, because it turned those stars into lighthouses of known strength. Hear the rhythm, and you know the true brightness. See how faint it looks, and the dimness tells you the distance. Leavitt had handed humanity its first tape measure long enough to reach outside the galaxy, and she was barely allowed inside the building. So when Hubble, with the largest telescope on Earth at his back, found one of Leavitt's flickering lighthouses inside the Andromeda smudge, the question of the smudges was over. Her rule gave the star's true brightness, its faintness gave the distance, and the distance put Andromeda far, far outside the Milky Way. The smudges were galaxies. The universe wasn't a building. It was a city of buildings, and nobody had ever seen past our own front door. And the city, it turned out almost immediately, was doing something nobody was prepared for. When astronomers split the light of those newly promoted galaxies, the colors came out stretched, shifted toward red, and nearly all of them at once, as if almost every building in the city were moving away from ours. Hubble, again with Leavitt's tape measure in hand, put the two facts side by side and found the relationship that now carries his name. The farther the galaxy, the faster it recedes. The universe is expanding. Not the galaxies flying through space like shrapnel, but space itself gently stretching between them, the way the distance between two raisins grows as the bread rises around them. A young Belgian priest and physicist named Georges Lemaitre had actually worked all this out on paper before the measurements caught up, and had followed the logic to its extraordinary conclusion: if everything is drifting apart today, then yesterday everything was closer, and once upon a time, everything was together. Run the film backward far enough, and you arrive at a beginning. The expanding universe, and the Big Bang waiting behind it, walked into science through the same door as the galaxies themselves, and all of it hangs off the flicker of Leavitt's little stars. Tonight's staircase is climbable only because she counted its first steps. Andromeda is our next landing then, and it comes with its own gentle astonishment. It is about 2.5 million light-years away, and you can see it without a telescope, on a genuinely dark autumn night. It is a faint, elongated glow the size of several full moons, and it is, by a comfortable margin, the most distant thing human eyes can see unaided. When that light left Andromeda, there were no modern humans on Earth. Our ancestors were just learning what hands were for. The photons crossed 2.5 million years of empty space, and the last centimeters of their journey ended inside your eye. People sometimes say stargazing makes them feel small, but I'd put it the other way round. You are the destination. The universe's light has been traveling toward all this time. Small things don't get mail from 2.5 million years ago, before we leave the naked eye sky behind. Look up at it one more time with tonight's rule in hand. The rule that distance is delay, because it quietly turns the whole night sky into a clock shop. No two stars above you are showing the same time. The light of Sirius, the brightest star of winter, is about 9 years old. A little parcel posted while you were living a different chapter of your life. Polaris, the North Star, shines from around 400 years back, its light older than the telescope itself. And Deneb, one of the 3 bright corners of the Great Summer Triangle, burns so far away that the glow reaching your garden tonight likely left it well over 1,000 years ago, when the brightest thing humans could make was a bonfire. Stand under a dark sky, and you're not looking at a moment. You're looking at a choir of different centuries, all arriving at once, all pretending to be now. Astronomers never see the universe as it is. They see a layered photograph of everything it has ever been, and the deeper they look, the older the layer. Tonight we're simply going to trust that strange arrangement and ride it all the way down to the oldest layers of all. The Milky Way and Andromeda, it turns out, are not strangers. They belong to a little cluster of galaxies called the Local Group, a few dozen members, mostly small, drifting together through space like a loose flock of birds, all bound to one another by gravity. The Local Group is about 10 million light-years from side to side, and that number marks a quiet turning point in tonight's climb, because it is the first landing where gravity's grip starts to loosen. Below this scale, gravity holds things together in neat bundles. Moons around planets, planets around stars, stars in galaxies, galaxies in groups. Above this scale, something else begins, and the something else is what the rest of tonight is about. Because here's the question the 20th century found itself asking. Once Hubble's city of galaxies had sunk in, how is the city arranged? If you could pull back far enough, past the Local Group, past 1 million galaxies, past 1 billion, what would the map look like? And for decades, the honest answer was that nobody knew, because nobody had made the map. Galaxies had been counted, photographed, catalogued in their thousands, but a photograph of the sky is flat. It tells you where a galaxy sits on the dome of night, but not how deep it is. And without depth, there is no map, only wallpaper. Astronomers could name 100,000 galaxies and still not know whether the universe was arranged like scattered sand, or like froth, or like something no one had imagined. The most reasonable guess, the one nearly everyone quietly held, was sand. Sprinkle galaxies through space evenly, the thinking went. A little clumping here and there where gravity had gathered them, but on the whole smooth, the same in every direction, the same everywhere. This wasn't laziness. It grew out of a deep and honestly beautiful assumption called the cosmological principle, which says that the universe, viewed at a grand enough scale, has no special places, no center, no edge, no throne. Averaged over a big enough box, any region should look like any other region, the way a beach looks the same from any deck chair even though no two handfuls of sand match. Almost everything in modern cosmology is built on that principle. And it is not arbitrary. It's written into how we do the mathematics of the whole cosmos. And it has passed test after test. Hold on to it gently, because near the top of our staircase tonight, something enormous is going to lean on it. To find out whether the universe really was smooth sand, someone had to measure the depth of thousands of galaxies, one by one, and in the 1970s and 80s, a small team at Harvard decided to actually do it. The tool was redshift. Light from a galaxy that is rushing away from us gets stretched on its journey, its colors shifted toward the red end of the rainbow, and in an expanding universe, the farther a galaxy is, the faster it recedes, and so the redder its light arrives. Redshift is a depth gauge. Point a telescope at a smudge. Split its light into a spectrum. Read how far the colors have slid. And the galaxy tells you, in its own light, how deep in the ocean it swims. Do that for one galaxy and you have a number. Do it for a few thousand, and you have the first true three-dimensional map of our corner of the universe. So they did, galaxy after galaxy, night after night, year after year, a survey led by Margaret Geller and John Huchra. And it is worth pausing on what that work actually felt like, because we're spoiled now by robotic telescopes and terabytes. This was the era of one galaxy at a time. A night at the telescope might yield a couple of dozen redshifts if the weather cooperated, and the weather is under no contract to cooperate. Each faint smudge had to be found, centered, held steady, its feeble light gathered long enough to tease a spectrum out of it, and somewhere in an office afterward, a number entered by hand into a growing file. Geller and Huchra and their students spent years of their lives converting photons into columns of figures, with no promise whatsoever that the finished map would show anything but sand. That's the wager hiding inside every survey, and it's a wager of years. Mapmakers of the deep sky buy their tickets long before anyone knows if there's a show. And in 1989, when they plotted a big slice of their map, the smooth sand idea didn't just wobble, it fell over completely. Picture the plot itself, because it has become one of the quiet icons of science, and it deserves seeing in the mind's eye. The survey's slice of sky renders as a wedge, a fan opening outward from Earth at the point, each measured galaxy a single small dot placed at its true depth. A few thousand dots, hard-won over years. If the universe were sand, the wedge would fill evenly, a smooth grey mist of dots thickening with distance. Instead, the dots gathered. They traced arcs and chains and long connected strands, and near the middle of the wedge, the dots drew what several people independently described as a little dancing human figure. Arms flung wide, the pattern was that unmistakable. Astronomers passed it around the way you would pass around a strange photograph. There was structure in it that no one had ordered and no one could unsee. The map showed structure, not gentle clumping structure, vast and unmistakable. Galaxies weren't sprinkled through space like sand at all. They were gathered into immense glowing sheets and ropes. and between the sheets lay huge rounded regions with almost nothing in them at all. Emptinesses tens of millions of light years wide. And running across the map, side to side, was something nobody had a name for yet. A ribbon of thousands of galaxies, more than 500 million light-years long. A wall of galaxies. And that is exactly what they ended up calling it, the Great Wall. Today it is known as the Great Wall of Geller and Hukra. And it was, for a while, the largest single thing human beings had ever found. Sit with that phrase a moment, because tonight it becomes a refrain. The largest thing ever found. It's a strange kind of record, because it's not really a record about the universe. The universe isn't changing. It is a record about us, about how far our maps have crept out into the dark, and like every record of that kind, it was made to be broken. But before we break it, let's stay on this landing long enough to understand what we're actually looking at. Because the wall was not an accident, and neither were the empty spaces. What Geller and Hukra had photographed, without quite knowing it yet, was the skeleton of the universe. Astronomers now call it the cosmic web, and the name is honest. On the grandest maps, matter arranges itself into a three-dimensional web of filaments, threads of galaxies, millions of light-years long, meeting at bright knots where clusters gather, wrapped around dark, rounded hollows called voids, where almost nothing lives. The shape of the foam is not an accident, and the reason it forms walls at all was worked out by a Russian physicist, with a name worth saying slowly, Yakov Zeldovich. He asked what happens when a vast, slightly uneven cloud of matter starts to collapse under its own gravity, and found something delightfully specific. A lumpy region almost never shrinks evenly, like a deflating ball. It always collapses fastest along one direction first. Squash a cloud along one axis and you get a sheet. The sheets then drain along their own surfaces into ribbons, and the ribbons drain into knots. Sheet, ribbon, knot, wall, filament, cluster. Cosmologists called the sheets Zeldovich pancakes, because physicists name things when they're hungry, and the prediction came years before any survey could check it. Then Geller and Hukra's map came back full of walls, exactly as the pancakes required. The universe builds walls for the same reason. Spilled batter spreads flat. Collapse plays favourites among directions. So when tonight's giant turns out to be wall-shaped, of all things, that's not a strange coincidence. Walls are what gravity makes first. If you want a picture to fall asleep to, make it this one. The universe, at the largest scale, looks like foam, like the froth on a bath, or a sink full of soap bubbles, with all the galaxies living on the soap film and all the bubbles insides empty, except the bubbles are hundreds of millions of light-years wide, and the film is made of galaxies the way a sentence is made of letters. Spend a moment inside each half of that foam, because both halves reward a closer look, and we now know things about them that Geller and Hukra could only guess. Take the empty half first. The voids are not merely gaps between the interesting parts. They are most of the universe, by volume the overwhelming majority of everything, and they are emptier than almost any emptiness we can make in a laboratory. The largest well-known one, the Borealis void, is a rounded hollow some 330 million light-years across, containing only a scattered handful of galaxies where tens of thousands would be expected. One astronomer famously remarked that if the Milky Way had formed inside it, we wouldn't have known other galaxies existed until the 1960s. Imagine that version of us for a second, a civilization growing up on an island so remote that the ocean shows no other shore, working out physics and music and bedtime stories under a sky that is one galaxy deep and then simply dark. Their astronomers would have been wrong about the loneliness of the cosmos, through no fault of their own. And it is worth remembering, kindly, that every sky is misleading from somewhere. Now the crowded half. A wall of galaxies up close is not a wall in any brick-and-mortar sense. If you were dropped into the middle of the Sloan Great Wall, you would not see a barrier stretching across the sky. You would see roughly what we see from here. Black space, scattered galaxies, generous distances between them. The wall only exists at the scale of the map, the way a rush-hour crowd only looks like a river from a helicopter. Nobody standing in the crowd feels like water, and the galaxies in a wall aren't cemented in place. They drift, they swirl slowly around shared centers of gravity. They collide over billions of years and pass through one another like slow ghosts, stars almost never touching, because even inside a galaxy, the gaps between stars are absurd. A wall of galaxies is less like a structure and more like a weather system, real, mappable, enormous, and made entirely of motion, and there is a hidden ingredient holding the whole web together, which deserves its own gentle confession. Most of the web isn't made of anything we can see. When astronomers weigh the universe's structures, by watching how fast galaxies orbit and how sharply light bends as it passes, the visible stars and gas come up short, drastically short, and the ledger only balances if every filament and knot is wrapped in a much larger scaffold of invisible matter, 5 times more of it than everything that shines. We call it dark matter, which is another of astronomy's honest names for a mystery, and in the standard picture, it is the true architecture of the cosmic web. The dark matter web formed first, and the galaxies condensed inside it afterward, like dew forming along the threads of a spider's web at dawn. What Geller and Hutter mapped, what every survey since has mapped, is really the dew. The web itself has never been seen directly by anyone. Tonight's whole story, in other words, takes place on the lit surface of a mostly invisible thing. And I mention that not to unsettle you, but because it makes the maps more impressive, not less. We've charted the shape of something we cannot see by the glow of what clings to it, and the web has a memory. That's the part I find genuinely moving. The pattern wasn't imposed on the universe. It grew from the smallest thing imaginable. In its very first moments, the cosmos was almost perfectly smooth, a hot, dense fog of matter and light, the same everywhere to within 1 part in 100,000, almost the same everywhere. Not exactly. There were tiny flickers, little quantum trembles in the fog, regions a hair denser than their neighbours, and gravity, which is nothing if not patient, went to work on that hair's difference. A slightly denser region pulls a little harder, so it gathers a little more, so it pulls harder still, and over 13 billion years and change, those microscopic trembles have been amplified into the walls and webs and voids we map today. The cosmic web is the baby photo of the universe. Enlarged, every filament of galaxies is a quantum whisper that gravity has been repeating, louder and louder, for 13 billion years. We know this isn't just a pretty story, by the way, because we've rerun the childhood. Inside supercomputers, cosmologists build model universes. They fill a virtual box with matter sprinkled almost evenly, seasoned with exactly the kind of tiny trembles we measure in the afterglow of the Big Bang. Switch on gravity and let simulated billions of years roll by in a few weeks of computing. And out of that almost smoothness, without any further instruction, the foam assembles itself. Filaments reach across the box and find each other. Knots brighten, voids inflate and empty out. Set a real survey map beside a simulated one and you can barely tell whose universe is whose. It is one of the quiet triumphs of modern science. And it hides a comfort I want to hand you directly. The largest pattern in existence grows from the smallest seeds physics allows, by nothing more exotic than patience. The universe is, at heart, a very slow gardener. Remember the gardener, because the entire mystery waiting at the top of this staircase comes down to a single question about her. How big a plant can she possibly have grown in the time she's had? Our own address in the web, by the way, was only properly worked out in 2014, when a team led by Brent Tully mapped the flows of thousands of galaxies, watching which way each one drifts, the way you might map a landscape by watching which way rainwater runs. Every galaxy whose drift leans toward the same deep basin, they reasoned, belongs to the same watershed. And our watershed turned out to be enormous. 100,000 galaxies, 520 million light-years across, all leaning gently toward a hidden center of mass. They named it Laniakea, a Hawaiian word meaning immense heaven. And it might be the loveliest fact on tonight's whole staircase. You have an address in immense heaven. You, your bed, your street, your planet, your galaxy, all of it belongs to one named region of the cosmic web, the way a village belongs to a valley. And since we're admiring the address, it's worth knowing that the web's architecture doesn't wait for the grand scales. It starts right outside our door, and our own little corner has structure with a name so good it deserves rescuing from the journals. The local group, it turns out, lives on a flattened arrangement astronomers call the local sheet, a thin plane of nearby galaxies, our first hint of wallness, only a few dozen million light-years across. And ringing that sheet, encircling us at a radius of roughly 24 million light-years, stand a dozen large, bright galaxies arranged in a rough circle that their discoverer named the Council of Giants. 12 great galaxies, seated around our neighborhood like elders around a fire, each one 100 billion suns or so, holding their positions for billions of years while our little flock of dwarfs huddles in the middle. It's mostly poetry, of course. The council doesn't govern anything. The circle is an accident of local history, but it means the pattern of tonight goes all the way down as well as all the way up, sheets and rings and gatherings at every scale, from the 12 giants around our campfire to a wall across 1/10 of the sky. The universe repeats itself at every size it owns. We just happen to live at one of the sizes that can notice. And the valley has a current. This is the part of our address that's genuinely strange to think about from a bed that feels so still. We are moving. The Milky Way, with all of us aboard, is falling through space at roughly 600 kilometers every second, drawn along Laniakea's slopes toward a distant concentration of mass astronomers call, with unusual drama for astronomers, the Great Attractor. For decades, its exact nature was maddening to study because it happens to lie roughly behind the crowded plane of our own galaxy. In that zone of avoidance where the Milky Way's glare hides the deep sky, as if the one signpost everyone was drifting toward had been deliberately placed behind the one lamppost nobody can see around. Modern maps have filled in much of the picture, a rich knot of galaxy clusters doing the attracting, with even larger concentrations beyond it doing some pulling of their own. But keep the sensation rather than the details. Right now, while your body lies perfectly still and heavy on the mattress, the room around you is coasting through the cosmic web at more than 2 million kilometers an hour, riding a slope carved by the largest landscape there is. Stillness, it turns out, is just motion too smooth to feel. You've been traveling all your life. Now, a reasonable sleepy question at this point is, does it just go on forever then? Walls, then bigger walls again, all the way up. Like one of those dreams where every door opens into a larger room? And the 20th century's answer, the official answer, the answer the mathematics of the whole cosmos leans on, was no, there's supposed to be a ceiling. Remember the cosmological principle, the promise that at a grand enough scale the universe becomes smooth. Every region like every other? For that promise to hold, structure has to stop somewhere. Zoom out far enough. And the foam should blur into an even grey, the way a knitted blanket, held at arm's length, stops being stitches and becomes simply a colour. Astronomers even gave the crossover a name, and it might be the most poetic name in all of cosmology. They called it the end of greatness. The end of greatness is the scale beyond which nothing new should appear. Past it, No walls, no webs, no shapes, just the same cosmic average repeating politely in every direction, forever. Based on the physics of how structure grows and on how much time the universe has had, theorists could even put a rough number on the biggest thing gravity should have been able to build since the beginning, and the logic behind the number is homely enough to hold before sleep. Structure grows by falling. Matter drifts down gravity's slopes toward matter. And the speed of that drift is limited, hundreds of kilometers a second at the grandest scales, magnificent by earthly standards, but a crawl next to the size of the universe. For a region to become a coherent structure, its parts need time to feel one another and gather. And in 13.8 billion years, moving at falling speed, there is simply a maximum reach, a horizon of acquaintance beyond which two regions haven't had time to so much as tug on each other properly, let alone assemble into anything shared. Work it through carefully, as theorists did, and the ceiling lands somewhere around 1 billion light-years, give or take, with one widely cited calculation drawing the line near 1.2 billion. Anything much larger than that simply shouldn't have had time to form. 13.8 billion years sounds like a long while, but gravity is slow, and matter is heavy, and a structure is not built faster than its parts can fall together. And how do we know the blanket really does smooth out rather than just hoping it does? Because the smoothing has been measured, and the measurement is one of the loveliest confirmations in science. Surveys like Sloan let cosmologists do exactly the arm's-length test with mathematics. Take boxes of different sizes, count how much the contents vary from box to box, and watch what happens as the boxes grow. Small boxes, a few million light-years wide, differ wildly. One holding a cluster, the next holding nothing. Bigger boxes differ less, and somewhere past a few 100 million light-years, the differences genuinely settle down toward a calm cosmic average. Region matching region matching region, just as the principle promised. The universe really does become a blanket if you hold it far enough away. That is precisely why oversized structures matter so much. The smoothing is real and measured, which means anything that refuses to smooth out at several billion light-years isn't a detail, it's a stitch the size of the blanket. There's an even deeper witness to the smoothness, and it happens to be the oldest thing anyone has ever seen. If you look out far enough, past every galaxy, past every wall, you eventually reach a glowing curtain. The afterglow of the Big Bang itself, light released when the universe was just 380,000 years old, still arriving from every direction after 13.8 billion years on the road. Astronomers call it the cosmic microwave background. And it's the actual baby photo I keep referring to, a full-sky portrait of the infant universe. And the portrait's headline is Smoothness. Across the entire sky, its temperature matches itself to about 1 part in 100,000. The trembles we met earlier being the tiny exceptions that grew into everything. The universe, at the beginning, was very nearly the same everywhere. That's not an assumption, it's a photograph. So the cosmological principle rests on the firmest possible foundation at the start of time. And the only real question, the question our wall sharpens to a point, is how lumpy the middle of the story is allowed to get on the way from that smooth beginning to tonight. So that was the rulebook as the new century opened. The universe is foam, the foam has a maximum bubble size, and the end of greatness is real. And to be fair to the rulebook, the next few record breakers politely obeyed it. In 2003, the Sloan survey, a robotic telescope in New Mexico, methodically measuring 1 million redshifts, revealed the Sloan Great Wall, a ribbon of galaxies about 1.4 billion light-years long. Bigger than anyone expected, close to the line, but arguably within it. And notice, painted into that story, a promise about the future. The sky still has curtains. The Milky Way's glowing band and its lanes of dust screen, a generous stripe of the deep universe, from ordinary telescopes and structures of any size could be waiting behind it. Astronomers peer through the gaps with radio waves and infrared, which shrug off dust, and every survey of that hidden stripe finds furniture nobody knew the room contained. The southern sky, historically surveyed more thinly than the north, keeps yielding surprises of its own. Whatever tonight concludes about our wall, hold on to this cheerful certainty. The census of giant things is not finished, not remotely, and some of the largest entries may currently be sitting behind the one galaxy we cannot ask to move. Years later came the South Pole Wall, about the same size as Sloane's, and its discovery carries a detail I love. It had been hiding behind the Milky Way. Our own galaxy's dust and glare blot out a whole stripe of the deep sky. Astronomers call it the zone of avoidance, and one of the largest structures in the known universe was tucked exactly there, the way the biggest thing in your bedroom can hide behind your own hand if you hold it close enough to your eye. The Sloan survey itself deserves a sentence of appreciation before we move on, because it changed the scale of the wager entirely. Where Geller and Hucra gathered galaxies by the dozen, Sloan's purpose-built telescope in the New Mexico desert gathered them by the plateful, hundreds of spectra in a single exposure through a clever plate drilled with hundreds of tiny holes, one hole per galaxy, each hole hand-plugged with an optical fiber by daytime staff who never saw the sky their fingers were mapping. Night after night, plate after plate. The survey measured its way past 1 million galaxies, and the maps stopped being slices and became volumes, great wedges of the universe rendered in confetti. Every structure in tonight's story after 1990, more or less, swims somewhere in Sloane's confetti, or in the surveys it inspired. If the 20th century learned that the universe has architecture, the 21st opened the full set of blueprints. Records crept upward. The line held, more or less. The foam behaved. And then a small team of scientists, who weren't even mapping galaxies, who were studying something else entirely, found a shape in the sky that did not creep past the line. It ignored the line completely. But to understand what they found, you first have to meet the strange and violent lighthouses they were using to find it, because the biggest object in the universe was not drawn by starlight, it was drawn by explosions. The story of those lighthouses begins, of all places, with the Cold War, and it is one of the great accidental discoveries in the history of science. In 1963, at the height of an arms race that had both superpowers testing bombs in the upper atmosphere and even in space itself, the nuclear powers signed a treaty banning such tests, and the United States, subscribing to the old maxim of trust but verify, launched a series of satellites called Vela to do the verifying. Vela means watch from the Spanish, and watching was their entire existence. Pairs of them circling high above the Earth, back to back, one eye on the planet and one on the sky, waiting year after year for the telltale flash of gamma rays, the most energetic form of light that a nuclear explosion produces. They were built as treaty police. Nobody involved imagined they were building the first gamma-ray observatory in history, and there is a gentle irony worth savouring in what happened next. Instruments designed to catch humanity at its most destructive ended up discovering the most powerful explosions in the universe, and found that none of them were ours. The satellites watched, and they saw flashes. Brief, brilliant bursts of gamma rays, again and again, over the years, dozens of them. But the flashes were wrong. They did not match the signature of any bomb, and they weren't coming from Earth, or from behind the moon, or from anywhere in the neighborhood. They were coming from the sky. From everywhere in the sky. In 1973, the discovery was finally published, and astronomy acquired its strangest new mystery. Something, somewhere, out in the universe, was going off like a flashbulb in gamma rays, at random, roughly once a day, and nobody had the faintest idea what it was. Picture the scene at Los Alamos when the flashes were first being puzzled over, because it deserves picturing. A physicist named Ray Klebesadel and his colleagues whose job was watching for treaty violations, sat with printouts of gamma-ray counts, comparing the arrival times at different satellites the way you would locate a thunderclap by comparing when different friends heard it. The triangulation kept pointing up and out, away from Earth, away from the sun, away from anything on any map. These were weapons engineers, in a sense, discovering by accident that the universe itself was detonating something, somewhere, on a roughly daily schedule, and had been all along. Nobody had predicted it. Almost nothing in astronomy arrived so completely unannounced. The universe had been running a fireworks show for its entire history, and humanity only noticed because we were watching each other. They were named gamma-ray bursts, which is the kind of name you give something when you know nothing about it, except what it is made of, and how briefly it lasts. For 20 years, the mystery only deepened, and the deepest question was the simplest. How far away are they? Because distance is destiny in astronomy. If the bursts came from nearby, from inside our galaxy, they could be something modest, little hiccups on neutron stars. If they came from far away, from other galaxies, then for the arithmetic of brightness to work out, each flash would have to be almost unthinkably violent. The sky offered one clue. The bursts arrived evenly from every direction. No preference for the plane of the Milky Way, no clustering toward downtown. Either they were very close, wrapped around us like a halo, or they were cosmically far, spread across the whole deep universe. Astronomy held a formal debate about it in 1995, and it settled nothing, which is the polite way debates usually end. Then, in 1997, satellites finally caught a burst's fading afterglow quickly enough for big telescopes to swing over and measure its redshift, its depth in the ocean of space, and the answer landed like a hammer. The bursts were coming from billions of light years away, from most of the way across the observable universe, and that meant the flashes were, and remain, the most powerful explosions known to occur in nature. A single gamma-ray burst, in the few seconds it lasts, can outshine every star in every galaxy we can see. Combined, if one went off in our corner of the galaxy, pointed our way, it would be brighter than the sun despite being thousands of light years away. In the whole history of the universe, nothing since the Big Bang itself has burned brighter, and each one is over in about the time it takes you to read this sentence. There's a burst worth telling on its own before we explain them, because it makes the brightness personal. In March of 2008, a burst went off in the constellation Borealis, and for about 30 seconds, its visible glow was bright enough to see with the naked eye. No telescope, just eyes. Anyone standing under a dark sky at that moment, looking the right way, could have seen a faint new star flicker on and fade out. Nothing remarkable, you'd think. People see faint stars all the time. Except that when the distance measurements came back, that little glimmer turned out to have travelled 7.5 billion light years. 7.5 billion. More than half the age of the universe. It remains the most distant object human eyes have ever been able to see unaided. And the ordinary record holder, our lovely Andromeda, at 2.5 million light years, was beaten that night by a factor of 3,000. For half a minute, the deep universe was visible from a back garden, and then it politely switched itself off. If you ever needed proof that these explosions belong in a different category from everything else in the sky, it is that one, an object at the far side of half of everything, briefly competing with the porch light. We know now, more or less, what they are, and both answers are strangely beautiful. The longer bursts, lasting from a couple of seconds to a few minutes, are the death cries of giant stars. A star dozens of times heavier than the sun, at the end of its short, furious life, runs out of fuel and collapses, its core folding up into a black hole in a fraction of a second, and in the chaos of that collapse, The newborn black hole launches two jets of matter and energy that drill outward through the dying star and erupt from its poles at nearly the speed of light, twin beams of gamma rays sweeping across the universe like the beams of a lighthouse. The shorter bursts, over in under a second, come from something rarer still. Two neutron stars, the ultra-dense cinders of dead suns, spiraling into each other and merging, a collision so violent it wrinkles space itself, and, as a parting gift, forges heavy elements and scatters them into the dark. The gold in a wedding ring was very likely made in a flash like that. Either way, a gamma-ray burst marks the most dramatic moment in the life of matter. And either way, it can be seen from almost anywhere in the observable universe. And that last part is what makes them useful to tonight's story, because think about what a mapmaker needs. Galaxy surveys like Sloan are magnificent, but ordinary galaxies grow faint fast. Map with starlight alone, and beyond a certain depth, the ocean simply goes dark. Gamma-ray bursts don't fade into that dark. They're bright enough to be seen across 10 billion light-years and more. Little pins of light sticking out of the deepest deep, and each one marks a place where a massive star lived and died, which means each one marks a galaxy, whether or not we can see the galaxy itself. Fireflies over a dark landscape. You can't see the meadow, but every blink tells you where the meadow is. Watch enough blinks, over enough years, and the invisible landscape starts to sketch itself. One honest footnote belongs to the fireflies before we follow them, and the discoverers themselves would insist on it. Bursts are not perfectly fair census takers. The long ones prefer a particular kind of home, smaller galaxies of an old-fashioned chemistry, still furiously making stars, which means the meadow they sketch is weighted towards certain kinds of neighborhoods and quiet about others. For most purposes, that is a technicality. A crowd of bursts still means a crowd of galaxies, because even picky fireflies need meadows to blink in. But it earns a place in your mental drawer marked things careful people worry about. And it will come out of that drawer later tonight, when the arguing starts. A reasonable sleepy question arrives here, and let's meet it head on so it does not follow us up the stairs. Should we worry about these things? If a burst can outshine galaxies, what happens if one goes off nearby, pointed at us? The honest answer is soothing. The events that make bursts need special ingredients, enormous rapidly spinning stars of a particular old-fashioned chemistry, or pairs of dead stars locked in a shrinking orbit. And our neighborhood is a quiet, middle-aged suburb poorly stocked with either. The nearest candidates astronomers occasionally mention lie thousands of light-years away, their aim uncertain, their schedules measured in hundreds of thousands of years, and even then a hit would be a bad day for the ozone layer, rather than an ending. Some researchers have wondered whether a burst long ago contributed to one of Earth's ancient extinctions hundreds of millions of years back, and it remains exactly that, a wondering, unproven, and probably unprovable. So, file gamma-ray bursts where they belong tonight. Not as a hazard, but as the universe's brightest census, takers, always far away, always long ago, and, as it happens, about to redraw the map of everything. So humanity built a firefly catcher. In 2004, NASA launched a satellite called Swift, named for the bird, because its whole talent is turning quickly. It watches a huge swath of sky, and within about a minute of catching a burst, it swings its telescopes onto the fading glow and pins down where, and with follow-up from the ground, how far, year after year, burst after burst. Swift and its companions have been filling in a slow pointillist painting of the deep universe. Each dot the death of a giant star billions of years ago. It is worth spending a minute inside one of those detections, because the choreography is wonderful, and it happens, on average, most days of the week. Somewhere over the Pacific, say, at 3 in the morning, Swift's wide-eyed burst monitor catches a spike of gamma rays. Within seconds, without waking a single human, the spacecraft calculates a rough position, swings itself around, and locks its sharper telescopes onto the fading glow. Within a minute or two, an automated alert is racing across the ground. Robotic telescopes on mountaintops in Chile and the Canaries and Hawaii read the message and slew toward the coordinates on their own. And phones buzz on nightstands in a dozen time zones because there are astronomers who volunteer to be woken for this. The way country doctors once slept with their boots by the door. The urgency is real. The afterglow fades fast, and the redshift, the depth, the number that turns a flash into a mapped point in the universe, has to be caught while the embers are still warm. Somewhere, a bleary human being pulls up a spectrum at 4 in the morning, reads how far the colours have slid, and types a distance into a circular that the whole world's observatories share. Each new burst gets a name stamped from its date, and the naming is so plain it loops back around to lovely. A burst caught tonight would be GRB, followed by the year, the month, the day, and a letter for its place in the day's queue. No heroes, no crowns, just timestamps, a diary the sky keeps in explosions. One entry at a time, going back half a century now. Somewhere in that diary, filed under unremarkable dates from the 2010s, sit the 20 entries this whole night turns on. By breakfast, the catalogue is one firefly richer. It is one of the quiet marvels of our era, a planetary reflex arc, built by hand, that flinches toward every dying star in the visible universe. By the early 2010s, that reflex had filled the catalogue with a few hundred bursts with good distances, scattered, as expected, across the whole sky and across billions of years of cosmic history. Scattered, as expected, almost everywhere. And now, at last, we can climb to the top of the staircase. Because in 2013, a small team of astronomers, Istvan Horváth, John Hakila, and Zsolt Bogoli, 2 Hungarians and an American, sat down with that catalogue and asked it one modest question. It was the same question Geller and Huchra had asked of their galaxies a generation earlier. Are you spread evenly, or are you gathered? They sorted a few hundred bursts by depth, sliced the sample into layers of cosmic distance, and checked each layer for clumping against the smooth, even scattering the rulebook promised. Layer after layer behaved, and then one didn't. In one particular slice of depth, the bursts refused to be even. In that slice, far too many of them, on the order of 19 or 20 out of the few dozen in the layer, crowded into one region of the northern sky, a patch covering the constellations Hercules and Corona Borealis, when an even universe should have placed only a handful there. The team ran the statistics again. The clump stayed. They tested it against the quirks of the catalogue. There's a detail from the discovery I find endearing, and it belongs in the record. They weren't looking for it. The team's actual research program was a quiet statistical question about whether gamma-ray bursts come in distinct families, long ones and short ones and perhaps an awkward middle child, the kind of tidy classification work that fills careers without ever making a headline. Checking whether the bursts scattered evenly across the sky was close to routine, the statistical equivalent of sweeping the floor before closing up. Horváth has described the moment the Hercules clump first surfaced with the plainest sentence in science. They did not expect it. Nobody goes fishing for the largest object in the universe in a tidiness check. And when the clump refused to leave, the team did the properly boring thing, which is the properly right thing. They spent months trying to make it go away, testing it against every bias and accident they could imagine, and published only when it would not. Keep that order of operations in mind later, when the doubters get their turn, because it matters that the discoverers were their own first doubters. Now walk through what that clump means. if you take it at face value, because this is the whole discovery in 3 quiet steps. Each burst marks a dying giant star. Each dying giant star marks a galaxy. So a crowd of bursts, packed into one patch of sky, all at around the same depth, marks a crowd of galaxies, a colossal concentration of matter, sitting at that depth. The depth itself deserves a word, because 9 to 10 billion light-years back is not a random address in cosmic history. It lands near the era astronomers call cosmic noon, the universe's great rush hour, when galaxies formed stars at perhaps 10 times today's rate, and the cosmos blazed at the busiest it has ever been or will ever be. Giant stars lived and died in unprecedented numbers then, which means gamma-ray bursts rang out in unprecedented numbers too. So it is natural, expected even, that the Firefly catalogue glows richly at that depth in every direction, and the discoverers knew it, which is why their test was never simply, are there many bursts at this depth, but rather, within this depth, are they spread evenly around the sky? An even rush hour is just the universe being young. A one-sided rush hour, all the traffic crowding one district of the heavens, is something else. And one-sided is exactly what Hercules looked like. The bursts in the clump lie at distances of roughly 9 to 10 billion light-years. And here's how you turn a patch of sky into a size, because the arithmetic is friendly enough to do in bed. Hold your fist up at arm's length. That covers about 10 degrees of sky. The clump of bursts sprawls across a region several fists wide, tens of degrees along its longest stretch. Now, the same angle means very different sizes at different depths, which you already know from everyday life. Your thumb can cover a passing fly or the full moon or a distant mountain, and the angle is identical while the objects are absurdly different. So take that generous handful of sky, project it out to a depth of 9 or 10 billion light-years, and ask how wide something must truly be to span that angle from that far away. The answer is what stunned everyone. At that depth, its true size comes out at somewhere around 10 billion light-years across. 10 billion. The Sloan Great Wall, the record holder that had seemed to strain the rulebook, is around 1.4 billion. This thing, if it's real, is roughly 7 times longer, set against the entire observable universe, which spans about 93 billion light-years from edge to edge. This single structure would stretch across roughly a tenth of everything there is to see. One object, one connected province of galaxies, a tenth of the visible universe long. That phrase, the observable universe, deserves a minute of unpacking before we lean any more weight on it, because it hides 2 ideas people rarely get to hear, explained gently. The first is that the observable universe is not the universe. It is the bubble of it we can see, centered on us, its radius set by how far light has managed to travel since the beginning. The whole universe may be vastly larger, possibly without end. We simply live inside a sphere of visibility, the way a diver, at night, lives inside the reach of her torch. The second idea is the puzzle you may have already felt twitch. If the universe is 13.8 billion years old, how can our view stretch 93 billion light-years across? Shouldn't the torch beam only reach 13.8 in each direction? The answer is that the water has been moving. Space itself has been expanding the entire time the light was in transit, carrying the distant regions farther away while their light swam toward us, so that a galaxy whose light travelled for 10 billion years now sits much farther away than 10 billion light-years. The road stretched behind the traveller. Add up the stretching honestly and the edge of the visible. The place whose light set out at the very beginning now lies about 46.5 billion light-years away in every direction, giving our torch beam bubble its 93 billion light-year width. So when we say the wall spans a tenth of the observable universe, understand it in those torchlight terms. One single object, reaching across a tenth of everything any observer here could ever, even in principle, see. And there is one more comparison that belongs to this channel in particular, because if you've spent other nights here, you've met the universe's other famous giants, and the wall resets every one of them. The most monstrous black hole in the catalogues, the one whose size fills entire videos, is a shadow you could lay end to end more than 100 billion times along the wall's length. The largest single galaxy ever measured, a giant that swallows our Milky Way 40 times over, would need to be lined up roughly 2,500 times to cross it. Even Laniakea, our entire immense heaven, the supercluster that contains 100,000 galaxies including everything you have ever known, would fit along the wall about 19 times. Every heavyweight the universe has ever entered into our record books becomes a rounding error against this one entry. That's what it means to move up a landing on tonight's staircase. The champions of the floor below don't compete anymore. They disappear into the carpet. Let's also try, gently, to inventory what a province that size would contain, because the census is worth hearing even if every figure wears a question mark. The observable universe, by the best modern counts, holds somewhere around 2 trillion galaxies. Carve out the wall's share of that volume, a slab 10 billion light-years long and some billions wide and deep, and even the crudest arithmetic hands you a residence of hundreds of millions of galaxies, plausibly more. Hundreds of millions of galaxies, each holding, on rough average, some 100 billion stars, which stacks up to a number of suns some 20 digits long, a figure with no everyday name, all belonging to a single connected object. If planets follow stars there the way they do here, and everything we have learned says planets are the rule rather than the exception, then the wall contains more worlds than there are grains of sand on all the beaches of Earth, multiplied by more than the number of people who have ever lived. And every one of those worlds had its sky, 9 or 10 billion years ago, and some of those skies had rain, or methane snow, or double sunsets, and whatever else they had. They were real evenings on real worlds inside the biggest thing there is. We can't name a single one of them. We can only know, statistically, serenely, that the wall was never just a wall. It was hundreds of millions of neighborhoods. They needed to call it something. And this is where I have to lodge tonight's one complaint, because the largest known object in all creation deserved a name with some thunder in it, and what it got was a map reference. It was named for the constellations its patch of sky happens to cover. The Hercules Corona Borealis Great Wall. Say it once, and you can feel your grip on it loosening. It doesn't fit on a poster. It barely fits in a sentence. I half suspect that is the real reason you've never heard of it, that the biggest thing in the universe has spent a decade filed away under a name like a dentist's paperwork. Astronomers themselves mostly shorten it to 4 letters, and for the rest of tonight, so will we. The wall, or when we are being formal, HerCRBGW, the Great Wall of Hercules and Corona Borealis, the biggest object in the universe and the worst named thing in the sky. In fairness to the poor wall, astronomy has never been good at names, and it can join a distinguished club of the badly labelled. This is the science that looked upon a colossal collision of galaxy clusters and named it El Gordo, the Fat One, that catalogues its most fascinating planets under license plate strings of letters and digits, that calls one distorted spiral the Meathook Galaxy and nicknamed a magnificent cluster merger the Sausage. Some of those names, at least, have charm. Our wall drew the shortest straw of all, a name with neither poetry nor humour, just coordinates in Latin. If the discoverers had felt 1 ounce more mischief that week, we might all know this thing already. The way everyone knows the Death Star or the pillars of creation, because a name is a handle, and things without handles are hard for a civilization to carry. While we're being honest about why you have never heard of it, the name is only half the story, and the other half says something rather lovely about how fame works in astronomy. The famous objects of the deep sky are famous because they photograph well. The pillars of creation, the ringed glory of Saturn, the burning eye of a spiral galaxy. Each one owes its celebrity to a single gorgeous portrait you can hang on a bedroom wall. The wall can never have a portrait. It is too large to fit in any telescope's view. Its galaxies are individually too faint to see at that depth. And its shape exists only as dots in a statistician's catalogue, a scatterplot, which is the one genre of astronomical image that has never once gone viral. The biggest object in the universe is, in the truest sense, camera-shy. It can be known but not photographed, calculated but not framed. And in an age where a thing becomes real to us by being seen, an unphotographable giant simply slips through fame's net. There is a quiet lesson folded in there, worth keeping beside the other treasures of tonight. The universe does not arrange its wonders in order of how easy they are to look at. Some of the greatest things ever found live only in columns of numbers and are no less enormous for it. Let's try to actually hold this thing for a minute. Because 10 billion light years is a number that slides straight off the mind unless you give it something to grip. Bring back the dinner table Milky Way. Our whole galaxy shrunk to the size of a pizza. On that scale, with our entire 100,000 light-year galaxy sitting on a table in front of you, the wall would be a shape stretching about 30 kilometers down the road. A pizza on your table, and a single connected structure reaching from your dining room to the next town but 3. That's the ratio between our galaxy, which already contains hundreds of billions of suns and every human story ever told, and this one object. Or make it personal instead. Light, the fastest thing permitted to exist, the thing that crosses your bedroom in a nanosecond and reaches the moon between 2 heartbeats, needs 10 billion years to travel from one end of the wall to the other. When light set out from the far end of it, the Earth did not exist yet. Sit inside that for a moment, because it means the entire biography of our world fits inside this one beam's journey, with room to spare. The light was already 4 or 5 billion years along when a cloud of dust near an unremarkable spiral arm collapsed into our Sunday. It kept traveling while the Earth cooled its crust, while the oceans filled, while the first cells learned their first tricks, while the air slowly turned to something breathable. It was still traveling through the age of trilobites, through the ferns and the dinosaurs and the comet that ended them, through the ice ages, through every human life ever lived, through the whole of yesterday, and it finished its journey, after all of that, tonight, in a telescope, or in the idea of one. While you were getting comfortable, everything that has ever happened here happened while that light was in transit. The wall is not just a place. It's a stretch of history with galaxies in it, and our entire existence fits inside its commute. Here's a second model for the sheer duration of the thing, softer than kilometers and closer to where you're lying right now. Let the entire history of the universe be one night of sleep. You close your eyes at the Big Bang and wake, 13.8 billion years later, tonight. On that clock, the first galaxies switch on within the first half hour of the night. The wall's light, the light arriving at our telescopes now, sets out around 1/4 past the second hour, in the deep early part of the night when the universe is young and busy. Our sun doesn't ignite until well past halfway through the night, around the 5th hour. The dinosaurs live and die in the last 10 minutes. All of recorded human history, every pyramid, every poem, every person you have ever loved or heard of, happens in the final 100th of the final second before your alarm. And light spends nearly 6 full hours of that 8-hour night just crossing the wall from end to end. One object, wide enough to swallow most of a universe's bedtime. When something is that large, distance and duration stop being different subjects. The wall isn't big the way a mountain is big. It's big the way a lifetime is long. One small honesty about the measuring itself. since we are leaning on the number so heavily. When astronomers quote 10 billion light-years, they mean the wall's span drawn on today's map, with all of cosmic expansion's stretching included. Back when the wall's light set out, the universe was a fraction of its present size, everything closer together. So the matter of the wall occupied a smaller patch then and has been carried apart ever since, the raisins riding the rising loaf. There is no trickery in this. Every giant structure's size is quoted the same way on the same map. So the comparisons tonight are all fair ones. But it is worth knowing that a size like this isn't a stick laid against an object. It's a careful statement about where everything sits on the grandest chart we can draw, a chart whose paper never stops stretching while you read it. And it is worth asking gently what the wall looks like now, tonight, at the far end of those 10 billion years, because the honest answer is one of my favorite kinds. Nobody can ever know. The galaxies we detect there are portraits from the universe's crowded youth, an era when stars were being born at rates our tired modern cosmos can only remember. Since then, those galaxies have had 10 billion years to burn through their brilliant blue youngsters, merge with their neighbors, settle, redden, and calm down, the way galaxies everywhere do. The wall's present tense, whatever it holds, is unreachable by any telescope, even in principle. Because its present-day light will not arrive here for another 10 billion years, if it ever manages to at all in a stretching universe. We know the wall only as it was. The universe keeps its largest possession the way you keep a childhood photograph of someone you have lost touch with, perfectly preserved, permanently out of date. And the light-as time machine rule from the bottom of our staircase now pays its strangest dividend, because remember, the wall sits 9 to 10 billion light-years deep, which means we see it as it was 9 to 10 billion years ago, when the universe itself was only around 3 to 4 billion years old, a third of its current age, or younger. And that turns one problem into two. It's not just that the wall is too big for the rulebook. It's that it's too big too early. Gravity is patient, but it is not fast, and the universe's structures are supposed to grow like trees, small first, mighty later. 13.8 billion years, the theorists calculated, buys you a structure around 1 billion light-years long at the very most, and here, apparently, is something 10 times that size, already assembled when the universe had barely a quarter of that time to work with. Finding the wall at that depth is like finding a fully grown oak in a photograph of a nursery. The photo doesn't just contain a surprise, it contains a contradiction. So the discovery paper went out into the world, and the world of cosmology did exactly what it should do, which is squint. And here we arrive at my favorite stretch of tonight's whole journey, the part I promised you at the start, the argument. Because the single most honest thing I can tell you about the biggest object in the universe is that we are not sure it exists. Not in the way we're sure Andromeda exists, or the Sloan Great Wall. And the reasons for the doubt are not embarrassing to science. They're the best of science, and they make a better bedtime story than certainty ever could. Start with the size of the evidence. The map of galaxies that revealed the Sloan Great Wall was built from about 1 million measured galaxies. The map that revealed our wall was built from a few hundred gamma-ray bursts, spread over the entire sky and the entire depth of the universe, because that is all the universe had handed us by then. The bursts arrive roughly once a day, on nature's schedule, not ours, and only a fraction get good distances. In the particular slice of depth where the wall lives, the whole case rests on a few dozen points of light, and the clump itself on about 20 fireflies, asked to testify to the shape of a meadow 10 billion light-years wide. The signal in those 20 is strong, genuinely strong, but small samples are where statistics goes to play tricks, and every scientist alive knows it. And there's a subtler trap here, one of the loveliest ideas in all of statistics, and it deserves a minute of its own. It's sometimes called the look elsewhere effect, and you already know it from your own kitchen. Toss a handful of rice onto a dark floor and look down. Somewhere in the scatter, you will find a clump. You will always find a clump. Perfect evenness is the one arrangement randomness almost never produces, and the human eye is a clump-finding machine of uncanny skill, tuned by a million years of looking for faces in leaves and ripe fruit in trees. Now, the honest question is never, is there a clump? The honest question is this clump more clumped than rice has any right to be? And when you went looking, how many floors did you check? Because if you search enough patches of sky, in enough slices of depth, sooner or later pure chance will hand you something that looks magnificent, and it means nothing more than the rice meant. The discoverers knew all this, of course. They're statisticians. It is their home ground, and they ran the numbers with exactly this trap in mind, and concluded the clump still stood, with odds of arising by chance somewhere down in the small fractions of a %. But other teams, rerunning the analysis their own ways in the years since, have come back with the full range of verdicts. Some find the signal survives, some find it fades toward the ordinary, and at least one later study argued flatly that a structure that size, at that depth, shouldn't be believed on this evidence. The wall's reality, a decade on, remains what a careful scientist would call an open question, and what a sleepy one might call a beautiful maybe. It's worth slowing down to enjoy how statisticians actually wrestle a question like this, because the method is charming, and it is the closest science comes to a bedtime ritual. One of their favorite tools is a game of make-believe called resampling. You take the universe's actual deck of cards, the real catalogue of bursts, and you deal imaginary hands from it, thousands upon thousands of them, shuffling the sky each time. Same number of bursts, same depths, same everything, except each pretend universe scatters them at random. Then you ask politely, how often does pure chance deal a clump as tight as ours? If 10,000 shuffled universes produce a Hercules-sized crowd only a handful of times, the real clump starts to look meaningful. If shuffled universes produce one regularly, the real clump is probably rice on the floor. The discoverers dealt their thousands of imaginary skies and found the clump rare, down at the level of a few chances in 10,000 by some of their tests. Their critics dealt their own imaginary skies, with different rules about the deck, and found it less rare. And if it frustrates you that two careful teams can shuffle the same universe and disagree, welcome to the tender frontier of knowledge, where the answer genuinely depends on choices about the deck, and where everyone involved knows it and says so in print. Nobody is being sloppy. The evidence is simply still small enough to bend. There is also a middle verdict available, and quietly, it may be the most likely one of all, so it deserves its own moment. The wall might be partly real. The doubters' sharpest arguments attack the extremes, the claim of one single connected object at the full 10 billion light-years, and several of the reanalyses that dissolve the giant still leave smaller, genuine clumps standing in the wreckage. Concentrations 1 billion or 3 light-years across, which would be remarkable structures by any other night standards. In that ending, the wall resolves the way many legends do into something real that grew in the telling, not a continent but an archipelago, not the largest object in the universe but 2 or 3 of its larger provinces, standing coincidentally along one line of sight like hills aligned into a false ridge at dusk. The record would quietly pass back to the confirmed champions near the rulebook's line. The universe would keep its tidy principle, and the fireflies would still have found something worth finding. Even the wall's most modest possible ending, notice, is somebody else's headline. The discoverers, for their part, didn't simply publish and retire to victory. 2 years after the announcement, with the catalogue grown by fresh bursts, they reran the whole hunt on the larger sample and reported that the Hercules crowd was still there, still stubborn, still refusing to average away, which is exactly what a real structure should do and exactly what a fluke usually doesn't. In the years since, they have answered their critics point by point in the journals, testing the clump against new statistical attacks the way a shipwright tests a hull, and it has, by their accounting, held, none of which settles the matter. Their critics have accountings too, but it tells you the shape of the thing. This is not a wild claim abandoned by its authors. It is a defended position in a long, slow, courteous siege, and sieges like this one are decided by supplies, and the supply that matters here is fireflies. There's one more suspect to consider, and it's the telescope itself. Swift does not watch the whole sky equally. It has favorite neighborhoods, patches it happens to stare at longer for perfectly practical reasons, and a survey that looks longer in one direction will find more of everything in that direction, the way a fisherman who parks over one reef all summer will swear the whole lake's fish live there. The discoverers checked this too, comparing the wall's patch against Swift's staring habits, and reported that the exposure couldn't manufacture a clump like theirs. Their critics have poked at that as well. This is what real science looks like up close, by the way, and I think it is worth saying so plainly, because from the outside, science can look like a procession of confident announcements. Up close, it is this: a handful of people, a few hundred points of light, and years of patient, courteous argument about rice on a kitchen floor. Meanwhile, in a lovely twist, the runners-up kept arriving, and the first one came from the same toolbox and very nearly the same team. In 2015, Hungarian astronomers sifting the burst catalogue found 9 fireflies at a common depth of around 9 billion light-years arranged. Of all things, in a ring, a near circle of dying stars 5.5 billion light-years across, promptly named the giant GRB ring, also far too big for the rulebook, also argued over, and carrying the same caveats as its big sibling: a small count, a striking shape, and the standing reminder that a ring seen from Earth may be a shell or a chance necklace of unrelated beads. The deep sky, it seems, had decided that if it was going to tease the statisticians, it would do it in style. Galaxy surveys added the huge large quasar group, 4 billion light-years of bright galactic cores, disputed for exactly the same statistical reasons. And in 2025, astronomers working with an entirely different kind of map announced a new heavyweight, and the method deserves a nod of its own. Instead of counting galaxies one by one, they mapped the hot gas that fills galaxy clusters, gas so hot it glows in X-rays, so that each cluster shows up on an X-ray survey of the sky, like a lit window on a dark hillside, no galaxy counting required. Following the lit windows, they traced a chain of clusters stretching about 1.3 billion light-years, a knotted cord of them, and named it Quipu, after the knotted cords the Inca used to keep records, which might be the best name any structure in this story has received. And notably, this one is generally accepted as real, the largest structure anyone agrees on. Notice where that leaves the ranking. The biggest confirmed thing in the universe sits right around the rulebook's line, almost as if the end of greatness is holding. And floating above the whole leaderboard, 7 times larger, is our wall. The champion with an asterisk, either the greatest structure that has ever existed or the most magnificent coincidence ever found in a catalogue. Let's take one slow flight before the verdicts, purely for the pleasure of it, because you have earned a view. Close your eyes and rise, gently, out through the ceiling, through the roof, up past the weather and the thin blue rim of air, and keep going, not at light speed but at dream speed, which is faster, and doesn't argue with physics because it never signed the paperwork. The Earth drops away to a marble, the Sun to a bright coin, the whole solar system to a scatter of dust with a lamp in it. The Milky Way assembles beneath you into its slow silver spiral, then shrinks to a brushstroke, and now the galaxies come out like lights at dusk, first dozens, then thousands, and as you keep rising they begin to organize. You start to see it, the threads, chains of galaxies linking cluster to cluster, the glowing rigging of the cosmic web, voids opening beneath you like dark countryside between towns seen from a night flight. Rise further, and the web itself smooths toward texture, a glowing tissue filling everything, And there, spanning the whole window of your attention, one thread thicker and longer than all the rest, running on and on past every edge of the view. The wall, if the wall is there, 10 billion light-years of gathered light, draped across the deep like a garland across a dark hall. Hold the altitude a moment. Nothing up here makes a sound. Nothing up here has ever made a sound. Then let go and fall, slowly, back down through the tissue and the threads and the brushstroke and the dust, all the way back to the marble, the roof, the ceiling, the pillow. That whole descent from the largest structure in creation back to your own bed. And notice, you never once left the map. It's all one place. It always was. Before we weigh the endings, let yourself wonder for a minute what it would mean to behold this thing, if beholding were possible. Because the exercise is gorgeous and it costs nothing. Suppose you could float somewhere with a clear view and see the wall's galaxies all brightened enough to notice. It wouldn't look like a wall. It couldn't. From anywhere inside the universe, a shape 10 billion light-years long simply does not fit into a sky. It would wrap across it the way a coastline wraps around a swimmer, and you could never see it as it is, only as it was in slices of different ages, the near end as it looked 9 billion years ago, the far end older still, every part of the picture arriving from a different chapter of cosmic history. To see the whole wall at once, as a single object in a single moment, you would need to stand outside the universe itself, which is not a place. The wall is, in the strictest sense, a thing that can exist but never be witnessed, only reconstructed, only known, and spare a thought for the wall's distant future, because the story has a final act written into the physics, and it is gentler than you'd guess. The universe's expansion is accelerating. A quiet push cosmologists call dark energy is slowly winning its long argument with gravity. And at the very grandest scales, gravity is going to lose. Structures like Laniakea, and like our wall if it is real, were never fully bound in the first place. They're gatherings, not buildings, and the accelerating universe will gradually usher their members apart. Over spans of time that make 10 billion years look brisk, the great walls will thin, the foam will stretch, distant galaxies will slip one by one over the horizon of visibility, and the sky of the far future will grow simpler and emptier and calmer. Every neighborhood left alone with its own lights. Nothing crashes, nothing burns. The largest things that ever existed will end the way an evening gathering ends. Guests drifting home one at a time, and the universe, which spent its youth building the grandest structures possible, will spend its endless retirement letting them gently go. Even the biggest object in the universe is, on a long enough clock, a temporary committee. There is something almost tender about that. The universe's biggest possession, and the universe itself, has no vantage point from which to admire it, and no means, in the end, of keeping it. We, with our catalogues and our 20 fireflies, are the closest it has ever come to being seen, and permit one mirror image thought, because the wall has residents, or had them, and fairness runs both ways. Somewhere in that province, 9 or 10 billion years ago as we receive it, there were, in all statistical likelihood, worlds with chemistry ambitious enough to wonder. If any of them wondered in our direction, they faced exactly our problem in reverse. Our neighborhood's light, crawling toward them across the same impossible gulf, showing them not us but our region's remote past, and any mapmakers among them, plotting their own fireflies, might have found our corner of the cosmos clumping in ways their rulebooks disliked, and argued about whether we exist. Two sets of statisticians, separated by 10 billion light-years and 10 billion years, each politely doubting the other's reality across a gap neither can ever cross. If the universe has a sense of humor, it is very patient, and it works at very long range. And spare a thought for the travel arithmetic, one last absurdity for the collection. Our fastest spacecraft would need well over 10,000 years to cross a single light year. Crossing the wall, end to end, at that pace, would take more than 100 trillion years, 10,000 times the current age of the universe. Even light, setting out tonight from one end, would arrive at the far end long after every star in every galaxy along the way had burned out. The wall cannot be crossed by anything we could ever build. And even light, setting out tonight from one end, would spend far longer than the universe's current age on the road. Arriving, if the stretching road lets it arrive at all, to find every star along the way long dark, it is not a place you could go. It is a fact you can only fall asleep inside of. So which is it then, continent or coincidence? Let's give both endings their moment, because tonight genuinely does not know, and there's a kind of peace in that. If the wall is real, then the universe has some explaining to do. The cosmological principle, the smooth blanket promise that underwrites our best mathematics of the cosmos, would need an amendment, or at least a very long footnote. Cosmologists would have to ask how so much matter gathered itself so early, whether the primordial trembles were less even than we believe, whether gravity had help, whether the recipe we have written for the universe's first act is missing an ingredient. A single object would quietly demand a revision of the biggest story we tell. And to be fair to the theorists, they wouldn't be starting from nothing. There are respectable doors to knock on. Perhaps the trembles in the baby photo weren't quite as innocently random as the simplest theory assumes, and carried subtle correlations that gave gravity a head start in a few enormous regions. Cosmologists have a name for that possibility, and have been hunting for signs of it for years for entirely separate reasons. Perhaps the wall is not one gravitationally knitted object at all, but a loose chain of great structures caught mid-assembly. A mountain range rather than a mountain, which would soften the collision with the rulebook without quite dissolving the wonder. Or perhaps, and this is the door nobody enjoys opening late at night, our neat calculation of the biggest allowed structure leans on an assumption that is only mostly true, and the universe is telling us, in its politest available dialect, that mostly true isn't the same as true. Every one of those doors leads somewhere interesting. That is the thing about oversized discoveries. Even their maybes are generous, handing out research careers in every direction regardless of how the original argument resolves. And if the wall is not real, if the clump dissolves as the catalogues grow, then tonight has been about something just as human and nearly as grand. The way 20 points of light and a pattern-hungry mind can conjure a continent. The way the same instinct that once drew a hero and a crown onto the summer stars drew one last colossal figure there, and how science, given time, can tell the difference. The ancient Greeks looked at that patch of sky and connected a scatter of unrelated stars into Hercules kneeling and a crown thrown into the heavens. We looked at the same patch and connected a scatter of dying suns into the largest object in creation. One of those constellations, at least, is imaginary. It may yet turn out that both are, and honestly, I'm not sure which ending I'd rather have. And notice while we hold that thought, that these are simply the two ways human beings have ever had of holding a sky. The old way was stories, take the scatter, find the figures, hand them down, and let each generation add its heroes and its crowns. The new way is catalogues. Take the scatter, measure it, test it, and let each generation add its rows and its error bars. It's tempting to call one of these childish and the other grown up, but they're more alike than either likes to admit. Both begin in the same place, a mind refusing to accept that scattered lights mean nothing. Both produce maps that say as much about the mapmaker as the sky, and both, at their best, are acts of care, ways of visiting the same few thousand lights so attentively for so many centuries that the lights start to feel kept. The wall belongs to the second tradition, But on nights like this one, told slowly in the dark, it is allowed to live in the first for a while too. Think of tonight as the wall's first bedtime story. Every great object in the sky has needed one, eventually, and 10 billion years is a long time to wait for yours. There was, for the record, a brief flare of fame when the discovery was announced. For a week or so in 2013, and again as follow-ups appeared, the headlines tried their best. Largest structure in the universe, object that shouldn't exist, and the wall had its moment in the world's news feeds. But fame built on a superlative needs the superlative to hold still. And this one came with an asterisk that only grew. Journalists returned for a verdict, found the scientists still courteously mid-argument, and drifted off to stories with endings. Doubt, which is the engine of good science, is the death of good headlines. So the wall slipped back out of the culture, unresolved, unphotographed, unpronounceable, and settled into the strange fate we found it in tonight. The biggest claim in the history of astronomy, living quietly in a spreadsheet, waiting for enough fireflies to make up the universe's mind. Fame will come back around, one way or the other, on the day the argument ends. Until then, it belongs to the people who like their wonders unfinished, which, tonight, happens to be us. Step back for a moment and notice the shape of the whole story we have climbed through tonight, because the wall, real or not, is only the latest rung of a very old ladder, and the ladder itself might be the deepest pattern in this whole subject. Every age of humanity has drawn a line and declared, "Here, this is the top. This is the size of everything." For the villagers under the dome, the top was the dome. For the Greeks, a nest of crystal spheres with the stars pinned to the outermost one, tidy and closed, and only slightly larger than the Earth. For the astronomers of 2 centuries ago, the top was the Milky Way itself, one island of stars, adrift in a possibly empty forever. Then the smudges became galaxies, and the top leapt outward a millionfold in a single decade. Then the galaxies gathered into clusters, and the top moved again. Then came the first Great Wall, then the foam, then Laniakea, then walls that strained the rulebook, and now a maybe wall that ignores the rulebook entirely. And do notice the trend. Not once, in the entire history of looking up, has the universe turned out to be smaller than the previous generation believed. Not once. The revisions only ever go one way. If you were a betting person, and it was somehow possible to collect, the safest wager in all of science would be that today's map too is a floor and not a ceiling, and that something in tomorrow's catalogues will make our wall look provincial. The biggest object in the universe is a title that has never once been retired. It only ever changes hands. Either way, the wall will not stay a maybe forever, and the way the question gets settled is worth knowing, because it's already underway. The Firefly catalogue only grows. Swift is still catching bursts. New emissions and telescopes keep joining the watch, and every year the deep sky gains more pins of light. Statistics is a slow tide. If the wall is a mirage, the new bursts will land evenly around it and gently wash the clump away, the way more rice thrown on the floor buries the first lucky pattern. If the wall is real, the new bursts will keep landing on it, again and again, more than chance allows, and year by year, the maybe will harden into a map. Some night, perhaps 20 years from now, a burst will flare in Hercules, a telescope will measure its depth, a number will slot into a catalogue, and somewhere a tired astronomer will realize the argument is quietly over. That's how the biggest discovery in the history of maps will end. Not with a flash, but with a spreadsheet finally sighing. And the verdict may not even rest on gamma rays alone, because the mapmakers are coming at the wall's neighborhood from other directions too. New burst hunting missions have joined the watch. A French and Chinese satellite called SFOM now catches bursts alongside Swift. An X-ray sentinel called Einstein probe sweeps the sky with an instrument modelled on a lobster's eye. Which is a sentence I promise is true, and astronomers keep sketching plans for a mission designed to harvest bursts from the universe's very first billion years. Each year's catalogues reach a little deeper and count a little more evenly across the sky, wearing away exactly the sampling worries the doubters raised. Meanwhile, the galaxy surveys keep pushing their confetti outward. Instruments now measure tens of millions of redshifts, robotic fiber. Plates doing in one night what took Geller and Hukra a career, and the great observatories now beginning their decade-long sweeps of the whole southern sky will chart faint galaxies by the billion. Somewhere in this generation of maps, the region behind Hercules and Corona Borealis will finally be surveyed richly enough that the wall must either stand up out of the data in person, galaxies and all, or fail to appear where 20 fireflies swore it stood. It is a rare and rather beautiful situation, a mystery with a guaranteed expiry date, one that will be solved not by a genius or a breakthrough, but by the simple accumulation of careful nights. Patience discovered the wall, patience doubted it, and patience will settle it. There are worse lessons to fall asleep on. Since we are headed to that patch of sky anyway, let's arrive the way the ancients did, through the stories. Because the two constellations standing guard over the wall have kept better names than the wall itself, and their stories make fine company at this hour. Corona Borealis, the northern crown, is a small, perfect arc of 7 stars, and it comes with a hidden jewel that suits tonight perfectly. Inside the arc sits a star called R Coronae Borealis. Ordinary looking, faintly visible through binoculars, with one strange habit. Every so often, without warning, it fades. Not a flicker, a plunge, dimming 1,000-fold over weeks, sometimes staying hidden for months before slowly climbing back. The cause, astronomers eventually worked out, is soot. The star periodically puffs out clouds of carbon dust, essentially smoke, that hang in front of it like a drawn curtain until starlight pushes the veil away. A star that hides itself in the constellation guarding a structure that may or may not be there at all. The sky does have a taste for theme. As for the crown itself, the Greeks said it belonged to Ariadne, the princess who saved Theseus from the labyrinth with nothing but a thread. When she later married the god Dionysus, he threw her jeweled crown into the heavens so the wedding would never be forgotten, and there it hangs still, a little circlet of light between the summer constellations, one of the few objects in the sky that actually looks like its name. And beside it kneels Hercules. And here's a detail I love. The constellation is ancient beyond its own myth. Long before the Greeks attached their strongman to it, older skywatchers knew that figure simply as the kneeler. A man down on one knee, name unknown, labour unknown, kneeling at the top of the summer sky for reasons every culture had to invent for itself. For thousands of years, humans have looked at that patch of darkness and felt somebody enormous was there, holding some enormous burden. And now, in a way no Bronze Age shepherd could have dreamed, the astronomers agree, behind the kneeler there may stand the single largest thing existence has ever produced. The shepherds got the size right, and were only off about the substance. And whichever way it goes, here's the part I want you to carry to the edge of sleep. You can point at it. Tonight, or the next clear night. This works. In summer, from the northern half of the world, go out after dark and look high toward the east and south. Find the brightest star overhead, Vega, hard to miss, and near it the keystone of Hercules, 4 modest stars in a crooked square, and just off to its side a small delicate arc of stars like a tiara, dropped on black velvet. Corona Borealis, the northern crown. Hold your hand up toward the space between them. Behind your fingers, behind those friendly nearby stars, behind 10 billion years of empty falling dark, lies either the largest single thing that has ever existed, or the most beautiful mistake in the history of astronomy. Your hand covers it completely, either way. That's the whole journey of tonight, folded into one gesture from a garden. A few practical notes for that gesture, so it actually works when you try it. City lights are no obstacle for the first step. Vega is bright enough to burn through almost any skyline, one of the first stars out after sunset in the northern summer, high in the east. The keystone of Hercules is fainter. 4 polite stars you may need suburbs or better to pick out, and the little crown fainter still. But here's the secret. You don't really need them. Once you have found Vega, the wall's patch of sky lies in the wide space to its west, and pointing anywhere in that generous direction is pointing at the wall, with room to spare, because the wall is not a needle to be threaded. It's a tenth of the universe. Precision is not the challenge. If you live in the southern half of the world, the whole tableau sits lower and upside down in your northern sky in the middle months of the year, Vega skimming the horizon from southern Australia. And if it never quite clears your rooftops, you have my permission to point through the planet. The wall doesn't mind. 10 billion light-years make a few thousand kilometers of rock beneath your feet into less than a rounding error of a rounding error. In fact, take that thought to bed with you, because it works from the pillow too. On summer evenings in the north, the wall's patch rides high overhead, so it hangs somewhere above your ceiling as you fall asleep, beyond the plaster and the roof tiles and the weather and the satellites, the quietest upstairs neighbor imaginable. By the small hours it has wheeled westward, and on winter mornings it sits below the horizon entirely, which means the straightest line from your sleeping body to the largest object in the universe runs down, through your mattress, through the bedrock, through the planet's molten heart, and out the far side of the world. Some nights you face it. Some nights you point your feet at it. It makes no difference at all. And that is rather the point. You can't be turned away from something that occupies a tenth of every possible direction's deep background. Wherever you are, however you lie, you are loosely aimed at the biggest maybe there is. Sleep has never once required knowing that. But it doesn't hurt to know it tonight. And while your arm is up, enjoy the full depth of what it is aimed through. Because that one line of sight is tonight's whole staircase, stacked into a single skewer. A few meters up, your ceiling, 100 kilometers up, the last wisps of air, 25 light-years out, Vega itself, its light 9 or so years younger than the light of Sirius, but a decade older than tonight. A few hundred light-years out, the stars of the keystone, then, hanging just off the keystone's edge, something worth knowing about. A faint fuzzy patch called M13, the Great Hercules Cluster, a swarm of several 100,000 ancient stars packed into a glittering ball about 25,000 light-years away, one of the oldest structures our galaxy owns. In 1974, humanity aimed the great radio dish at Arecibo precisely there and transmitted a message, a little pictogram of our numbers, our chemistry, our shape, and our address, the most powerful, deliberate broadcast our species had ever sent. It's still in flight. It has crossed barely 1/5% of the distance, and it will arrive, if anything is listening, in roughly 25,000 years. Past the cluster, the line runs out of the Milky Way entirely, through the realm of the galaxies. 2 million, 200 million, 2 billion light-years. Layer after layer of fainter and older light, and then, 9 billion light-years down the skewer, it enters the wall, and stays inside the wall for most of the remaining distance to the beginning of time. One raised arm, from a garden, threading a needle through everything from your bedroom ceiling to the largest maybe in creation. No other gesture your body can make covers quite so much ground. One more picture before we descend, a small one this time, human-sized, because tonight has earned it. Somewhere, in an office in Budapest or Charleston or wherever the work happens to live this year, there's a computer holding the catalogue. The actual file, the biggest object in the universe, as humanity currently knows it, exists most concretely as a modest table of numbers on an ordinary machine, each row a burst, each burst a dying star, 20 of the rows quietly agreeing with one another in a way that has kept careful people arguing for a decade. Some evenings, presumably, someone opens that file, adds the newest fireflies, reruns the old tests, and watches whether the clump stands a little firmer or a little fainter than last year. No dramatic music plays when they do. That is the true scale of the human end of this story, and I find the mismatch wonderful rather than sad. A tenth of the universe on one side, a spreadsheet and a cup of coffee on the other, and in between, nothing but honest method and 10 billion years of travelling light. The universe does the enormity. We just have to do the bookkeeping, and stay curious, and keep the file open. So let the staircase settle now, and drift back down it one last time, landing by landing, the way you came. Tonight you started under your own ceiling and stepped out past a moon still holding 50-year-old footprints, past sunlight that is always 8 minutes late, past the Voyagers still climbing their first light day. You crossed the hair's width to Alpha Centauri and watched the pizza-sized galaxy fill your table, every human story a dust grain in its quiet outskirts. You watched Hubble prove the smudges were cities, and Andromeda's ancient light end its 2.5 million year journey inside your eye. You saw the first great wall fall across a stick-figure map, the universe turn out to be foam, a quantum whisper enlarged for 13 billion years, and your own address written in immense heaven. You learned why the universe builds in walls at all, batter spreading flat under gravity's favourite directions, and you met the end of greatness, the polite ceiling where structure was supposed to stop. Then you watched a Cold War satellite's mystery become the brightest lighthouses in creation, saw one of them outshine half the universe for 30 naked-eye seconds, and watched 20 of those lighthouses crowd into one impossible corner of the northern sky, up where a kneeling hero guards a throne crown with a star that hides behind its own smoke. A wall 10 billion light-years long, a tenth of everything visible, too big and too early for every rulebook we own, wearing the dullest name in astronomy, defended and doubted by careful, courteous people who all agree on just one thing. The universe is under no obligation to be the size we expected. If your thoughts are loosening by now, by the way, let them. Nothing ahead requires the earlier rungs. The staircase carries you whether or not you remember climbing it. And half-heard cosmology makes perfectly good dreams. For anyone still comfortably aboard, one final door remains, the softest and largest of all, and we only need to lean on it, not walk through. It is the question a child would ask at exactly this point in the story. If the observable universe is the torch beam, what's beyond the beam? And the honest answer is a shrug performed at the grandest possible scale. More, almost certainly. The edge of vision is an edge of light, not an edge of things. And nothing whatsoever suggests the universe stops where our seeing does. How much more is unknowable in the strictest sense? Perhaps a great deal more of the same. Perhaps endlessly more. An infinity of foam and walls and quiet bedrooms. And if the cosmological principle holds out there, the neighbourhoods beyond the beam look broadly like ours, webs and voids, and the occasional oversized maybe, forever. Our wall, the largest thing we have ever glimpsed, would then be nothing special at all, one stitch in a blanket without a hem, and there is something oddly restful in that demotion. Even the biggest thing might be ordinary somewhere. Even records at the very top dissolve into peace, and maybe that's the real gift of the biggest object in the universe, whether or not it exists. Every generation has drawn a line and called it the top. The dome over the village, the edge of the last map, one galaxy alone in the dark, a wall, a bigger wall, an end to greatness. And every generation, the universe has waited politely and then stepped over the line. Whatever the wall turns out to be, a continent of galaxies or a trick of 20 dying stars, it has already done its quiet work. It has reminded us that the staircase probably does not end where we can see it end, and that being small in something this large isn't a loss. It's the roomiest feeling there is. Now, there's nothing here you need to hold on to. No quiz waiting at the end of the universe, no names to remember, not even the long clumsy one. Let the walls and the fireflies and the foam all drift apart again, the way rice settles on a dark floor, slowly, softly, in no pattern at all. Let your shoulders loosen. Let your breathing find its own easy rhythm, the way the deep sky keeps its own slow time. Somewhere very high above your roof, between a kneeling hero and a thrown crown, the biggest maybe in the universe is holding perfectly still. And it will hold perfectly still all night, whether anyone watches or not. You can leave it there. It's been there for 10 billion years. It will keep. If you're still awake and you'd like one more journey, there'll be another one waiting on the screen to carry you onward. Otherwise, just stay here in the quiet.